This is a flexibility of what we call VLANs. That is, between different floors, we can achieve. Different floors can communicate across switches. Let's discuss how VLAN is implemented. I now ask you a question. Port of this switch. Different devices are connected under it. For example, now both of them are not in the same VLAN. Then please. The device on the left acts as a PC. Does it know whether it is in the same VLAN as the device on the right when sending data? Okay. It doesn't know. So for end users, we only guarantee the most basic data communication. Specifically, what VLANs are they? It doesn't care. So when the PC is actually sending data, it doesn't know which VLAN it is in. It is totally unknowable. The operation of VLAN is configured on the switch. It is a technology deployed on the switch. Let's take a look at the process. For example, now PC1 sends a broadcast ARP. Suppose it wants to ask a user on the same network segment 1.2 of this MAC. Because we did not configure the gateway, we will not go to the third floor for now. The device on the left sends an ARP to ask the device on the right. The switch received the ARP data. How does it tell which VLAN it is based on this data? For example, I now assign 1.1 to VLAN 10, 1.2 in VLAN 11. They do not belong to the same VLAN. Then this data should not be forwarded, although it is an ARP broadcast. But it belongs to cross VLAN. Then how does it know that this data belongs to VLAN 10? Everyone think about this question. The data sent by the PC does not know what VLAN it belongs to. I have to operate on the interface of the switch. That is, data is sent to the switch here. When coming in from the interface, we want to add a tag to this data. It is a field. The above is a standard Ethernet 2 message. A total of 18 bytes. This part is the frame header and frame tail of the second layer E2. Data is the data part. This tag is inserted between the two of them. This type indicates what protocol the upper layer is. This is the destination MAC and source MAC in the second layer. And checksum. Then the overall tag is embedded in the overall data frame. The tag is not just a VLAN ID. It contains a lot. But these things are not very important. First there is a TP ID. It represents the 802.1 queue we will talk about today. 802.1 queue is also called .1 queue. We will configure this thing when we do configuration today. It is a data encapsulation standard. Is a type of publicized tag. Cisco actually has its own proprietary, called ISL. But we hardly use this now. In fact, the proprietary technologies of various manufacturers are not used very much. We are now using public. So it identifies the what kind of tag type do we use. Further down here there is a priority. It represents the priority of VLAN data. In the future, you will learn the IE stage. Learn this field when you learn QoS. Let's not look at this stage. Further down is CFI. It represents whether this frame is a standard format. A CFI of 0 represents the classic format. A CFI of 1 represents a non-classic format. It's almost classic now. So we don't need to look at these parameters now. The most critical is this VLAN ID. This is the switch. This is a PC. PC sends a data. When the data arrives at the switch interface, the PC will carry the VLAN ID. Then there is a 12B written in the VLAN ID. Represents 12 bits. VLAN ID has a range. 12 in total. Each bit has two values 0 and 1. This represents the number of VLANs you can create on the switch. You divide an interface into a VLAN. A data enters this interface. Enter the corresponding VLAN ID. This VLAN has a range. Each bit has two values 0 and 1. There are 12 bits. A total of 2 to the 12th power. A total of 4096 combinations. That is a total of 4096 VLANs. But 0 to 4095. This is a total of 4096. Start from 0. Computer languages start with all zeros by default. So it ranges from 0 to 4095. Among them, 0 and 4095 cannot be used. The VLANs we can create are 1 to 4094. This is the range of VLANs we are able to use and create. Remember this. You have no way to create a VLAN larger than 4094. In addition to the VLAN ID we mentioned above, there is another concept. Link type. Let's go back to this picture. For example, we are not giving this device an IP address now, regardless of whether it is a network segment. Assume now go through layer 2 communication. The data arrives at the switch here. Since the behavior of this tag is done by the switch, then think about it. It sends this data to the PC on the right with this tag. Assuming they are both in the same VLAN. Can you send it over? Okay. This is not allowed. Let's take a look at this picture. First you need to know. PC can't recognize tag. I had a student ask me a question before. PC does not recognize the tag. Then don't look at this field. Okay? Just skip it. What I want to say is, our equipment is not so smart. The data frame read by the device is 01010101. A normal data received by PC. After reading the destination MAC and source MAC, you should continue to read type. So if the device sends a data frame with tag, other devices will interpret the data frame according to the type. Then it will find that it does not understand. Because there are 2 bytes in the original type. The first 12 bytes have been read. The 2 bytes of type should be read. As a result, these 2 bytes have been read. It found that this does not seem to be type. Then it means that the data frame cannot be understood. If you don't understand, there is no way to read this data frame device. If it can't be recognized, it can only be thrown away directly. Because reading data is read one by one, including the type in the second floor of our study. The protocol in the 3 layers. It's all about pointing out what the upper layer is now. For the sake of, after reading the second floor, if the third layer is the IP protocol, to read one by one field in the IP header, there are rules. So we often say, the lower layer indicates the upper layer, is for upper class service. When data is read, do you know what kind of data encapsulation standard to read the upper layer data? So this tag is sent to PC. It has no way to recognize. This packet can only be lost. Therefore, it cannot be sent to the PC with the tag. This thing is only recognized by the switch. I said it before. VLAN is deployed on the switch. Only the switch can recognize it. The router can also recognize. But you have to do other configuration. Today we will talk about how to configure. So what we should do is tag the data when it comes in. For example, type a tag 10. In the future, this interface will also be tag 10. Data to be sent. Then when the data leaves this interface, remove this tag 10. Equivalent to. You now want to identify whether the 2 of them are in the same VLAN. Then both interfaces belong to VLAN 10. Tag when you come in. Then when the data flows in the switch, it carries the tag. Remove the tag when you come out. Then send to the terminal, so that they can be dealt with accordingly. It is reasonable to be able to do this technology. Otherwise, the technique is useless. All I want to say is, after we divide the VLAN, each interface will have its own link type. Different link types have different processing behaviors for data. Let's talk one by one. In fact, Cisco is better understood. Cisco only has two link types. The first is access mode. Access mode is used to connect to PC. Before talking about access mode, I should mention two other things. First of all, you need to know, the data frame sent by the PC is called the original frame. It has many names. The original frame is also called the blank data frame. Means data frame without tag. The data frame sent by the PC is always a data frame without tag. For switches, the switch will be flooding. The flooding principle of the switch will be on all except the receiving port. Flooding of other ports belonging to this VLAN. We just said, the switch receives data if flooding. Then it is all interface flooding. Because all interfaces are in the same VLAN by default, called VLAN 1. If the VLAN is divided in the future, an interface has received a data. For example, this unknown unicast is a broadcast. It will only flood the ports belonging to this VLAN. As for how to configure the port VLAN, we will demonstrate. For access mode, we'll connect some end devices, such as computer, server, printer, camera, etc., including future dedocking routers. In fact, we use the most access mode, because the router is a layer 3 port by default. It also cannot handle VLAN-related content. And for each interface, both directions, there are data receiving direction and sending direction. This sentence we will encounter in the future in the study. We are in the NA stage. In addition to the VLAN we talked about today, when it comes to ACL in the future, there will be the same data. We have received direction as well as send direction. One might ask, does the full switch have VLAN? The full switch has a VLAN 1 by default. A switch for dummies is also a switch. The default port of the switch belongs to VLAN 1. It also has its own VLAN. But it's just that it can't be configured. You can't configure other VLANs for it, since the data sent by the PC does not carry the VLAN ID. Then the data is inside the switch. How can I forward it with an ID number? We are through the VLAN ID of the interface. So the default port of the switch belongs to 1. After the device is received, the tag is 1. Let's draw a picture to explain. This is a switch. A PC is connected below. PC now wants to send data. It is connected to an interface of the switch. I assign this interface of the switch to VLAN 10. And it is connected to PC. The connection terminal is access mode. Now access is going to receive data. When it receives data, there is a specification. First look at whether the data has a tag. If no tag, then I'll tag it. This tag is the current VLAN 10 tag. If a data is received, it has tag itself. Everyone will find it strange. I said to connect the terminal under the switch. And if access mode, computers or printers are connected under the switch, they should not be switches. How can I send tag data to VLAN? This is also very simple. I will give you a simple example. For example, now this interface is connected to a PC or a virtualized server. Either now this PC or virtualized server. I opened a virtual switch for it. It is actually the same as a normal switch. If I now let it bridge the local NIC, then there is a switch here. If auto-negotiation is enabled on both ends, they can even auto-negotiate port. For example, this is an access interface. The data comes in with a tag. I let it bridge with the local network card. So finally there is a switch connected here. Then it can be sent with this tag. So there is also something called VLAN jumping attack. I open a virtual switch in the device. Negotiate with the above interface to become a trunk. This is VLAN 10. As long as VLAN 10 is allowed to pass through, its interface is a VLAN 20. It can skip VLAN restrictions and communicate with hosts below. It can all be done. But I haven't seen this thing in the project. In theory it is possible. I'm just giving you an example. PC can also send out tagged data. We are now because of the technology involved in virtualization. So many things are not so absolute. It is possible to receive tagged data. What if there is a tag? If you receive a tag with VLAN 10 now, then it receives and does nothing. That is, do not remove the tag. Any interface will never strip the tag in the receive direction, just to see whether to accept. If it belongs to other VLAN, then don't. If a VLAN 20 message is sent, it will not be accepted. This is a specification of it. Then let's draw. This data is sent now. Then tag it with VLAN 10. To be posted later. Send in our exchange. At some point it arrives at another interface. This interface is also VLAN 10. It is also an access mode. It is also connected to a PC under it. So what is its forwarding principle like? How does access operate when sending data? Very simple. When sending data, first look at the tag in this data. Is it the same as the tag of this interface? If this tag is consistent with the VLAN of this interface, should send, and will strip the tag before sending. If this tag is inconsistent with this interface, don't send. Here's how it works. So we see if it's consistent now. The data comes in and is tag 10. Walk in the switch with tag 10. Finally, we will query the MAC address table in the switch. And the MAC address table also has the VLAN to which the corresponding interface belongs. So I can locate this interface. And I found that this interface is also 10. Then it is now consistent with this interface. So strip the tag and send. What comes out is a complete blank data frame. It's a simple process. Finally, the data of the original frame is sent out. For two PCs. What they receive is neat. They feel like the two devices are connected like this. Data forwarding. So for the middle. All about VLANs they are unaware. We'll get to that later. A router is connected to the switch. For routers. If you connect to the router normally in the future. For example, this is a switch. This is also a switch. A router connected to the switch. Then the port of this switch should be access. Because the final docking is a layer 3 interface. Layer 3 interface does not know VLAN. So you have to make sure. This tag must be removed when the data is exported. If even a router. In fact, it can also be identified. But you have to turn on other functions. Next, let's see how to configure. This thing is not difficult. This is 3 devices. It is now on the same network segment. Let's see if the same network segment can't communicate today. They are both 10.1. We will configure the mask to be 24 bits later. They are all on the 10.0 network segment. But both of them are VLAN 10. It is VLAN 20. So wait a minute, we divide the VLAN. Divide on these three interfaces. After dividing it should be. Both of them can pass. But it doesn't work with both of them. Because originally if we did not do any configuration, all three of them should be able to pass. Because they are on the same network segment, the switch does not need to be configured. Learn automatically. Then it's straight through. But after we divide the VLAN, it doesn't work. Let's see how they can't work today. Okay. Let's do some simple configuration. When we talk about the trunk later. Another type. Let's demonstrate access first. Device boots up. This is PC1. Give it an IP address. 192.168.10.1. 24-bit mask. PC can be configured like this. Just enter 24 later. You can also configure the full mask with. Let's take a look at the complete mask of the next configuration. Then PC2. 192.168.10.2. We can also configure like this. 3, 255 and 10. This is also possible. Next. PC3 will not be configured first. Let's look at the switch first. We come in first. Everyone will find. Inside Cisco. When the switch comes in. No need to manually enter NO first. You may be a little uncomfortable. For switches. After changing the name. Let's check its VLAN. Do show VLAN brief. Okay. Now the switch has a VLAN. Don't worry about these below. Let's just look at one. There is a default here. Then the switch is created by default. What do these all refer to? If you create a switch here. This has a default Ethernet port. It's a 4x relationship. If you write one, it will create 4 interfaces. Then actually, these are the 4 interfaces we created. All 4 interfaces now belong to VLAN 1. You did not configure anything. But these interfaces have their own VLAN ID. Is VLAN 1. All we have to do next is put 0 and 1 into VLAN 10. Put 2 into VLAN 20. That is, put these 3 interfaces respectively where they should be placed. First we have to create the VLAN. VLAN 10. VLAN 20. After creating, I strongly recommend that you do this. We can give the VLAN a name. Let's say it's called PC. PC is equivalent to adding a note to this VLAN. Let's check this VLAN. Show VLAN brief. It will have a name in the suffix. Behind this VLAN 10. It is VLAN 0010. This is a way of expressing. After 20. A PC is written here. This is the name we just gave this VLAN. For example, if you want to assign these VLANs to the technical department, just write a technology for VLAN 20. You write a financial statement for this VLAN 10. While you are viewing, the various departments can be divided according to these names. Check what VLANs the switch currently has. There was only VLAN 1 just now. Now with VLAN 10 and VLAN 20. This is what we created. After creating, we are now going to divide these interfaces into different VLANs. Enter configuration mode. First enter the 00 interface. That is, the interface of the switch connected to PC1. It belongs to VLAN 10. So how to change it? I teach you a command. Switch port mode. I enter a question mark. There is a private VLAN here. This you will learn in the NP stage. Then there is an access and a trunk. These are two types. There is another one that everyone is using now. .1Q tunnel. This you will learn in NP. We only learn these two in NA. Let's change the access now. We divide it into access types. Then after changing to the access type, we need switchport access again. We need to assign VLANs to it. VLAN 10. We can now look at this configuration. Do show run interface E00. OK. Let's take a look at its configuration. We first changed it to an access mode. Secondly, change it to VLAN 10. Here is the configuration for this interface. Then we exit. We also perform the same configuration for the 01 interface. The 01 interface must also be in access mode. Switch port mode access. Then switch port mode access VLAN 10. When we are done with this now, let's exit and take a look at the situation of the VLAN just now. Show VLAN brief. This is VLAN 10. Interfaces 0 and 1 in VLAN 10 have entered VLAN 10. Just these interfaces are in VLAN 1. After we divide, these two interfaces are in VLAN 10. Then we now first look at ARP on PC1. Here it shows that the ARP table is empty. Because we don't have data access right now, I can give a simple explanation. It's not working now. Both of them are VLAN 10. They don't span VLANs yet. We haven't configured yet. Let's review the process. For example, PC1 now sends a data here. Hit a tag 10. But let's not talk about the tag issue. What I want to ask you now is, for PC1. PC1 is 10.1. PC2 is 10.2. PC1 holds its own mask locally. Add the IP address of the peer. Calculate whether PC2 and PC1 are in the same network segment. Should be the same network segment. Then, if PC1 accesses PC2, it is now going to send an ARP request. That is, a broadcast packet. So now this message is sent. Sent to this switch. This switch first starts learning. Under this interface, I learned a PC1 MAC. After that, it is flooding the interface to which VLAN 10 belongs in the current device. Because it doesn't know yet. Where exactly does this broadcast packet go? But it's flooding. Flooding from its native interface belonging to VLAN 10. It localizes these two interfaces. Except that it received from the 00 interface. Then the broadcast data packet sent will only be sent from the 01 interface. That is, it will look up representations from here. Then post it. So we just finished creating VLAN 20 here. We now divide this 02 interface into VLAN 20. Let's configure. First enter the E02 interface. Switch port mode access. Switch port mode access VLAN 20. It is different from other equipment VLAN. Show VLAN brief. Check it out. Now for interface 2. It is already in VLAN 20. We also configure an IP address for the third device. 192.168.10.3. We now have 3 devices in the 10.0 network segment. Let's take a look at the message next. I asked PC1 to wait a while to ping PC2. Logically speaking, it works. Because VLAN 10 comes in here. Our ARP must first send a group. Then from this interface, the ARP broadcast should pass. It should come back with an ARP broadcast from here. After that, our ping packets will pass through. So let's wait a moment to get the packet under this interface. We can get ARP packets. This is the first point. Before we talk about VLANs, if by default all devices belong to the same VLAN, then this interface will also receive ARP broadcast packets. Because we're going to broadcast. Let's see now that the VLANs are divided. Will this broadcast be sent from this interface? So we can see. After the VLAN is divided. Is the broadcast data packet really unreachable? Let's take a look. We get a packet for interface 02. Let's do a demo. Let's get another packet from interface 01. Let's do a demo. This thing is not very important. Just to show you a phenomenon. You have to verify whether the knowledge is correct. Get the data packet of interface 00 and only see the reply from PC2. Which is equivalent to. Now this packet. It is to wait a while to reply. Including the package that will pass through ARP. This is through ARP. This is without ARP. We set our sights on this. Let's try to ping now. We start ping here on PC1. Ping 192.168.10.2. Ping PC2. Then what we should be able to see here. Okay. We see ARP. Same. Let's take a look at the message on the right. It has nothing. We pause. There is no need to read the rest of the messages. This is under the 01 interface. The one on the right is under the 02 interface. Under interface 02. It does not see any ARP packets. This shows that the ARP request is a broadcast packet. Then the broadcast message and the destination MAC should be all F. When PC1 requests the MAC of PC2, it doesn't actually know where PC2 is. So it broadcasts. If it is according to the statement that all interfaces of the switch are in the same VLAN. This broadcast packet is sent like this. Now this interface cannot get this broadcast packet. Because it belongs to VLAN 20. And they belong to VLAN 10. So when a broadcast packet comes in, tagged with VLAN 10, it is not issued from the interface of VLAN 20. So it cannot receive this message. ARP is a broadcast packet. When the virus spreads in the future, it is also a broadcast packet. Then the reason is the same. No matter what packet. I'll call 10 when I come in. Then the interface of 20 will not send out. In fact, we don't need to take a closer look at the content. Just read this message. Okay. We can also check the MAC address table on the switch now. Show MAC address table. We can only see the interface for VLAN 10 here now. That is 00 interface and 01 interface. Anyone know why we can't see PC3? Because PC3 has no data passing through the switch. Send data to broadcast here. PC2 replied. So both interfaces are learned. And they pinged a few times between the two. Messages flow between them. But this interface did not receive broadcast packets at all. It also won't reply. So we now want it to learn PC3's MAC. You should ask PC3 to ping out. For example, I let it ping 192.168.10.1. It definitely can't ping. PC1 must ping PC2 through. But it is definitely not possible for PC3 to ping PC1 and PC2. Not reachable. But it's definitely something that can be learned by now. There is a MAC under the 02 interface. It belongs to VLAN 20. So it is equivalent to learning all three now. But we also verified. Can communicate between them. It doesn't work with it. That's the same reason. It definitely doesn't work with 10.2. Because they cross VLAN. So this is what we call access. This is how it works. Everyone observe this MAC address table. The MAC address table I drew for you just now is relatively small. In fact, each of the MAC address tables is very useful. I just drew the interface and MAC address. It actually has VLAN. That is, how do I know which interface belongs to which VLAN? The MAC address table has. When you divide the interface into a VLAN, the VLAN corresponding to this interface will be written here in the MAC address table. So now a broadcast packet is sent from interface 01. I will only flood from other interfaces belonging to VLAN 10. So I can know. The data only goes out through the 01 interface. So this information is known by the switch itself. Because when it queries the MAC address table, in addition to looking at the interface and MAC address, it also looks at the VLAN. Dynamic means that the current MAC address is dynamically learned. Dynamic learning means that others send data to flow through it. In the future, you can also learn static binding. You will learn in NP. Let's do some port security. For example, a fixed MAC is connected under one port. Or we can also set up to connect multiple fixed MACs. If you connect a switch, there are many MACs below. It's okay too. Bindings also have dynamic bindings. You can also bind manually. This is all the content in NP. Now do a simple understanding. Let's talk about the process. If PC1 cannot access PC3 now, why doesn't it work? Let's review. PC1 accesses PC3. Then first PC1 thinks that PC3 is on the same network segment as it. Then send an ARP request. A broadcast packet goes here. Tag with VLAN 10. Then query the local MAC address table. Because it is a broadcast packet, so it should be on all interfaces belonging to VLAN 10. In addition to the receiving port. Flooding on other ports. Only this interface is issued. After receiving this interface. After reading the second floor. We need to look at the ARP in the 2.5 layer. There is a target IP inside. The target IP is to find PC3. But it's 10.2. So it won't reply. So PC1 cannot receive a reply. Because its request message can't reach PC3 at all. So it has no way to communicate with PC3. This is the basic forwarding principle of switches based on VLAN. Next we talk about trunk. If you are interested, you can make this kind of picture after class. This diagram is more basic. When we make a trunk, we directly make a more difficult one. We do one-arm routing. Trunk is the two switches. The difference between trunk mode and access mode is that, first of all, they have different names. It's obvious. Trunk means the main road through which more traffic will flow in the future. In the access mode, it is directly connected to the terminal. Then only terminal traffic will pass through this line. The trunk road is all based on the, like the picture in the courseware. Let me explain their names. Access link means this link is called an access link. This link will only run data belonging to the PC. Whether someone else accesses it, or is it accessing someone else's. This is actually equivalent to an access device. Trunk means now you don't care whether these two devices communicate with each other. The two devices communicate with each other. Or do these two devices communicate with each other? They all flow through the road in the middle. It's like what we call the main road. Now devices want to communicate with each other through it. The interconnection between each other is the same. This is also the trunk. We can also configure it as a trunk. So for us, where data flows through. It is equivalent to a trunk between switches and switches. The connection between the switch and the terminal is an access link. Only run your own traffic. So this is the difference in their names. Let's talk about trunk mode. Simply put, switch to switch. Here's what we call the difference between them. The biggest feature of trunk is it can host multiple VLANs. An access interface can only belong to one VLAN. The trunk can serve multiple VLANs. For example, now this is still a PC. Here is also a PC. PCs are connected to the interface of the switch. Also connected between the switch and the switch. A link used in the middle is called trunk. We connect to the terminal or access. For example, this is still access VLAN 10. Suppose the right side is still VLAN 10. Let's see how it goes. It's easy here. Let's not talk. Data comes in and hits here. There is another package in the trunk. Will be slightly different. We go in here first. Because what we use now is actually the same. After you come in, we will put tag 10 here. Then this data flows through other interfaces. For example, it is going to access this device now. Then the data will now go to this interface. When the trunk is sending data, there will be a difference. First, the trunk will have a release list. For Cisco, it will allow all VLANs by default. But please note, this allows all VLANs. It just means that the VLAN created on this switch will be released now. Assume that there is no VLAN 10 on this switch itself. Then the traffic of this VLAN 10 cannot pass through this interface. You must first create. You just create. It allows by default. Second, we will now check. Check whether this tag 10 is the same as this native VLAN. It defaults to VLAN 1. So now there is a VLAN 10 coming over. It checks whether it is the same as its own one. If the same, it will strip the tag. Send later. If different, do not strip the tag and send it directly. So now I don't modify it. Then come in is 10. If it is 1, send it directly. So actually, we are in the process of data transfer. It was sent back with tag 10. Then this data carries this tag. It came to the interface on the right. The right interface is also a trunk interface. Then when the trunk interface receives data, it will also have some processing behavior of its own. Handling behavior is simple. The first is to look at your release list. Also released all. So, when the data comes, it will receive it directly by default. But still that sentence. VLAN 10 must also be created on this device. Secondly, when we receive the data now, if the received data is received with tag, it just sees if it lets it go. If it is a raw data, that is, blank data frame, without tag, it will mark the native VLAN of this interface. Then you can send data, which is equivalent to the ones coming in now are carrying tag 10. So I took it directly. After receiving this data, continue to move forward. Go to this interface now. Since it is also an access interface, and is VLAN 10. Then here it will strip the tag of VLAN 10 to complete the forwarding. Send to another PC. Then in this process, if there are some other circumstances, for example, now this interface belongs to VLAN 20. There is no interface belonging to VLAN 10 on this switch. But I created VLAN 10. The data will come in. But it can't reach the destination. Because cross VLAN. What we are talking about is that if they are different VLAN, it sure doesn't work. But it's okay to send the data like this. It's just that it can't be sent from this interface. This is what we call a trunk. Let's talk about its configuration in a while. This is how it forwards.